Our next talk, the next speaker is also from psychology and neuroscience. Dr. Christoph Daube, who recently passed his PhD. Congratulations. He's going to talk to us about quantitatively comparing predictive models with information theory managers.
Okay, that works. So good afternoon, everyone, and thanks for sticking around even for so long, so late in this day. So this talk was originally supposed to be given by Robin Ince, my former PhD supervisor, I can now say. And Robin can't make it, unfortunately, today, so you have to bear with me, and I hope I can give an acceptable talk on his behalf on quantitatively comparing predictive models with information theory measures. Let's see if this works now. Yes. So on the first slide, I have this quick primer on information theory, and I'm pretty sure that the expertise on information theory in this room will vastly exceed mine by orders of magnitude. But nevertheless, I think it makes sense to kind of see that we're all on the same page with regard to the terms that are being used in this talk. So the very simple thing we can start with is we can draw one circle to represent one variable and quantify its entropy or its fancy variance. And then we can go on and have two of these variables and overlap them and quantify the statistical dependency and get to something like mutual information. Then we can enter the realm of three variable systems, which is the main focus of this talk. Or we can, for example, look at conditional mutual information. So we just condition something between two variables on a third variable. Or we look at something that is referred to as co-information, which is the triple set intersection, which will aim at quantifying interactions between these three variables. And the point here is that all these kinds of things were already around in the 40s and 50s, so back when Shannon and friends were inventing information theory from scratch. And what I'm sort of looking at in this presentation now is something that's surprisingly a lot more recent, where we start again with such information terms, and to relate it to this kind of conference, you could, for example, imagine that you have some predictive model that predicts some observed variable, and you have some predictions. And now you just overlap them and thereby see how well your model performs in a bivariate sense. And now you could imagine that you don't just have one of these, but you have two of these. So you have a different model that tries to predict the same kind of response variable. And now you might be interested in basically computing the overlap of overlaps. So the redundancy of these two models. So you want to know to what degree they actually predict your response variable in the same way. And once you do this, then you might also be interested in other so-called atoms of partial information decomposition, which are then unique information of one and the other model, and synergistic information that you will only get from jointly considering the two models together, or two feature spaces together. And as I said, so this is surprisingly more recent. So people started to look at this from this perspective of partial information decomposition only in 2010. And then, from there on, so there has been a lot of debate on how to actually quantify redundancy on a data set. And this debate, I think, goes on to the present day. Once you agree on one such measure, the other atoms fall out sort of from a pretty simple algorithm which people seem to agree on. Right, and so one such algorithm actually was, sorry, I don't know how to make this. Maybe it's, maybe I should just use this and maybe that's a bit better in terms of sound, I don't know. So one such algorithm was developed by Robin, and I like it quite a lot. It's called common change and surprisal. And so the idea that Robin had here was basically to, first of all, give mutual information a different name, namely sort of change and surprisal. So surprisal being another word for entropy. And if you think back of these things I was showing on the first slide, right, mutual information is just the degree to which your entropy changes of one variable, because now you know something about that variable. And if you then look at this change in surprisal about the target variable S, if you know predictor X, then you can resolve this on a pointwise level. So you look at pointwise mutual information, and these pointwise terms can be positive and negative. And now you do this not just for one sort of predictor, but also for another. And then you basically check across all your sort of samples in your data set where these terms have the same sign. The idea being, right? If two sort of predictors have different signs, then they can't be contributing the same information, whereas if they have the same sign, then that might be the case. And so Robin sort of says, look at this for the two predictors and also their joint and interaction information on the pointwise level, and sum it up for all cases where you sort of find these to be the same. So that's here and here. So one wants to get relevant information, one wants to get relevant misinformation, and then that's your global sum of the whole data set for this redundancy estimate. And then this seems to kind of make sense if we look at simple toy examples. For example, this suppressor effect, which is something psychologists like me really like. It's very simple. If you see here, we just have two predictors, x1 and x2, and one consists of s plus n and the other of n, and then our response variable y only consists of s, so it doesn't contain n. And now we can look at some classical approaches that people have been using to decompose shared and unique contributions to a prediction of y. And these would be, for example, variance conditioning, causality analysis, and classical information theory. So the stuff I was showing from the 40s and 50s. And you see they all seem to be agreeing that there should be some kind of similar pattern here, which is that you get a negative common part. That's kind of weird, I think, or doesn't mean to be negative. And then you get a positive unique part of x1. That's also okay, and a positive unique part of x2. That also is kind of counterintuitive because right, x2 only has this n, which doesn't even figure in y. So why should it be contributing anything uniquely to your response variable? Well, PID seems to be solving this to a much more satisfying result. So here we say we have actually a positive contribution of x1, and then dominate the synergistic part, which makes sense given this generative model where basically get better at predicting y with the two of them because we can isolate the noise in x2 and being separated from x1. So that's all fine and dandy. There's of course more ways to show that it kind of works, but this is one example. What can we do with this for science? For example, for cognitive neuroscience, which is what I'm interested in. So we can, for example, look at a data set that I recorded where 24 poor souls were sitting in our MEG scanner, where we record the magnetic field that is caused by neurons in the brain with these helium-cooled sensors. Not invasively, I shall say. And we did so while they were listening to an audiobook of 1 hour duration. And so the thing is, now you can sort of play this game of building encoding models where you try to predict the brain responses with different features of the story. So one option, for example, would be to consider acoustics of the story, right? So you have the spectrogram in blue, or this temporal derivative of the spectrogram in turquoise, all fairly simple. And then you build a predictive and linear model to project these features onto some dimension of interest and quantify your performance. And then you can repeat this exercise with different feature spaces, for example, from annotated features. For example, phonemes, which linguists take to be the minimally contrastive units of speech, where they change the meaning of a word, like cat versus hat, and so on and so forth. And people have shown that these phonemes seem to be contributing something more than just spectrograms of their own. And of course, it's kind of exciting now because these phonemes are much more cognitively challenging and high level and so on. And you can build nice stories about pre-lexical abstraction and how we understand speech by projecting something to something that linguists talk about when they talk about language and so on and so forth. So there's a whole host of sort of debates here. And now, of course, the kind of interesting question is, can we maybe account for this gain in prediction performance that we get from these phonemes from these simple acoustic measures? And we could sort of quantify this with this overlap of overlaps, so this partial information decomposition powered redundancy. And that's what we did. So in the first instance, we will just that's a bit of a bummer. There's something missing here. And this, I don't know why this happened, but for some reason, we don't see the actual results in this slide, which would have been that you would have seen posterior distribution of model performances, and they would have shown you that very simple models like the envelope and the spectrogram are on the left of this red sort of bar. That means they are worse than this combination of the spectrogram and the spectrogram and the articulatory features, which is these phonemic features. So we get a boost in prediction performance using the phonemes or the spectrograms on their own. However, if we then use the spectrogram in combination with the temporal derivative, we are better than this red line. And so that means, okay, we are just better in a bivariate sense, but does it follow from predicting different variants, or does it follow from predicting the same variants? Well, so we now perform this PID on these results using model predictions in different colored lines on this observed data and quantify this overlap of overlaps. And then we find that actually this spectrogram and sample derivative is really at 100% of explaining the same variance as this benchmark feature space, so this fancy cognitive high-level feature space. That's one nice result. Then we can also look at unique information, and there we see that actually the turquoise thing ends up having unique information which this red fancy feature space doesn't have. And now we can also turn the whole thing around. So we can not just play an encoding game, but also a decoding game where we try to infer something about the experimental sort of design, right? So the story from the brain responses. And so we can now take this observed data and, for example, decode phoneme classes from it. And that's sort of this ellipse in black. And now we can do the same thing from our model predictions, right? So the point being, if we can decode something from model predictions that is sort of redundant with what we decode from the observed data, then that means we don't need more than this simple model to account for this phenomenon of decoding something high level. So if you then time log the brain responses to these phoneme onsets, you get these nice different color shades, so different phoneme classes, which means you can, measure positive information about these phoneme classes at different time points following a phoneme onset. But you also get this if you just time log the responses of the simplest model, which is just time varying energy of the envelope that you filter through some FIR model that you estimate. And now this translates into sort of us being able to measure positive unique information from these model predictions of all the models, and only negative unique information, misinformation from this observed data. So we can basically account for everything that the observed data tells us about phonemes, and the observed data is just noisy and doesn't have anything on its own. So the point of this being, right, whenever you kind of find some paper that tries to say, right, we have some passive viewing or listening data, as many people have these days, and we have this fancy model, like some crazy deep network from the latest transformer or whatever, and now make a point about some high-level processing in the brain, then you always have a really hard time of just making sure that there isn't simple explanations for this tantalizing high-level phenomenon. All right, so that being said, we can look at a different application of PID. Where basically we don't have neuroimaging responses, but just behavioral responses from button presses, so human behavior in response to pictures of faces, and they come from a generative model, where this model controls them in terms of the RGB texture and 3D shape. And we can also feed these images into fancy deep networks and extract representation from them, and then build models of behavior from these deep network activations. And now again, you'll guess it, we will want to sort of see if PID can add anything to this picture, and why that would be interesting, I will try to motivate now. So if we think about the situation we're in, we basically have these 2D images that we show to our human, which is, am I muted? I don't know. Okay. Wow, I go through a lot of microphones today. So we show these pictures to this brain, which symbolizes our human, and he presses or she presses buttons, telling how similar this picture is to a person they know. And now we feed these into some DNN, extract representation from the DNN. We don't do this just for one DNN, but we have a couple of nets. We have a view invariant autoencoder, we have an autoencoder, we have multi-class classification, identity classification, triplet logs, what have you. Point being, we now have this model set, and we can compute predictions using activation from all of these deep networks that were trained without ever seeing the behavioral data. And now what? So now we get some model that performs best. Does this mean anything in terms of its similarity to how the human presses buttons in terms of evaluating the picture? Well, I guess we've seen previous talks today already, and you might know this example where I show this picture of a horse to some classifier, and it says, yeah, this is a horse. But if you look at which region in the image it's attending, then you see, yeah, it's attending this Lota lens Photoarchiv.de watermark in the bottom left. So it's using different features than humans would use to classify this. And as soon as you remove the watermark, yeah, your sort of identical behavior to the human is gone. So even if we measure sort of a good bivariate performance here, we can't really be sure that the model is even processing the same features as the human if we don't control the input. And that's exactly what we do. So we have this stranded model where we generate these spaces behind the wall of pixels in terms of 3D shape and RGB texture, and project it then on this 2D screen. And now we can also predict this the behavior in terms of sort of this experimental controlled 3D variance, for example, on every vertex. And then we get a map of how every vertex contributes in the 3 directions of space to a behavioral response. And the thing is, now we can compute this overlap of overlaps, so we sort of see, right, how far can we account for the modeling performance of our deep networks with these 3D shape features. And that gives us this 2D plot where we see the MI, so there's the bivariate performance on the y-axis. And then we plot that against this sort of redundancy with the shape features on the x-axis. And we see if a model gets better at predicting the behavioral responses, it seems to be doing so because it's kind of using features that are really also contained in the 3D shape variants, which we can control. And so we can then go through a bunch of, like in the long term, we can go through a bunch of models and test these and see what seems to be working and get a close idea of how human vision works. Okay, so that brings me then to my final summary slide, where I would say that in cognitive computational neuroscience, we often have many candidate models, right? So that, I guess, is true in many other fields. And we want to learn something about the brain or human behavior by comparing these models. And so partial information composition, PID, offers a principled approach to go beyond bivariate model comparisons and teases apart these redundant, unique, synergistic contributions of models. And so I would hope that, maybe this is also applicable to problems that you guys have, where you have some other machine learning problem and you're interested in some more nuanced understanding of how different feature sets or different models are contributing to your performance, right? So if you sort of have some big model and you have another big model, and now you're wondering, like, would it make sense to train something that combines these 2 big models, which you maybe can't even afford with your current small GPU? Then this tool might help you in assessing whether it might make sense, because you might have some synergistic interactions going on, or some unique interactions. So that's all from my side. Thanks very much for your attention, and I'm looking forward to your questions.
Okay. Okay, do we have any questions from the audience? Okay, I have one. So you said, like, we can look at the information from different models and we calculate this partial information metric. But how do we get what number is it in the model? How do you take feature maps and put them into a histogram so you can create a distribution to compare that mutual information in the first place? Do you have to do a transform or give it the same domain?
So this is kind of really like a very simple thing where you just operate in the prediction space and you just somehow magically arrive in a small low-dimensional thing by means of predicting something, which in our case is always low-dimensional. So we look at some relevant channel in the brain response that is low-dimensional, or some relevant human behavior that is one-dimensional, and then if you operate in that space, then things are very easy. Okay, you can just plug it into this function that is available in Python and MATLAB, I think. So
okay, thanks. Any other questions?
I was wondering, like, whether the mutual information you're considering is capturing some correlations in the data from the different models, or can it be used to actually capture the causal mechanisms and rid of the spurious correlations that may induce some false causation mechanisms?
I mean, I guess if I understand your question correctly, then I would say, for example, in the first example where we have this uncontrolled passive listening paradigm, right? So it's really hard to rule out any such thing. So you need extra constraints. Like I like parsimony, so I like this very simple model that then accounts for something very complex. But of course, that doesn't mean that that this parsimonious model is correct. It just means it's cheaper and maybe easier to apply this, for example, in hearing aids, where people are interested in reading out this brain response. And so they don't need to, build some crazy thing that arises in the phonics space, but they can use very simple acoustic transformations. That doesn't mean it's, what's happening for real. So that's why it's still the same problem. And then the other idea we have is basically, which is not our idea, which is, okay, we have to do experiments. Like, okay, wow. But so do experimental manipulations, which I think was mentioned in one of the very first slides of the very first talk, that this is always a trade-off if you go in a naturalistic direction or in a control direction. But I think somewhere with this combination, you're on a good way. MI is just fancy correlation, so
Okay. Well, thanks again to Christoph. That was a great talk.